Hi, how are you? Let me pull up the assignments for this week and have a look at that. And I have to close the door so that I can limit interruptions. Um, okay, so today, this is what's happening this week. We had the electric circuit CER that was due on Monday, then the suggested one that was due on Tuesday on Coulomb's law, and then we have delayed the inquiry stations. The nail lab I put in instead, and that is due today by midnight. Electromagnetism CER that was put off until Monday, and then the extra credit assignment on Earth's magnetic field is also due today. I do want to say that people have been submitting assignments in the ones that have been archived, so I will not continue to be grading those. The deadline on the assignments from before spring break was April 30th. So this is a whole week later. So I'm not continuing to see that I can remove those assignments without totally removing the assignment from the classroom and without affecting the grades for students that have done that. So I will try to get to that today. Today, I want to go over a little bit of series in parallel, some problems that I've been seeing with the work that you have done on series in parallel. And then I want to talk about transformers and power transmission. All right. And then sometime this weekend, I will try to post something about Earth's magnetic field for those of you that are interested. I find that's kind of the purpose of learning all this stuff is how does it affect our lives directly? Well, Earth's magnetic field is huge in our lives here on Earth. So let's start with the series in parallel, the issues that I saw from assignments with the series in parallel, understanding of that. So I've gone ahead and I've written up the rules again. So I want to talk about this a little bit. So series is a one-way path. If we look at the circuit here, we start at the battery, we go to the first bulb. We cannot get to the second bulb without going through the first one. Continue on our way through the wire to the second one, and we get all the way back to the voltage source. So a complete path, you have to go through both of those. If one of those is out, then the other one will not light. All right, so there was a big problem with that. If one of the bulbs goes out in a series circuit, the other will not light. Okay, one-way path. Current is the same everywhere. So if both these bulbs are identical, they have the same current, so they have the same brightness. Resistance adds up. So the more things that you put in your circuit, the greater your resistance. You're increasing your resistance by adding more resistors. In this case, if we're talking about the CER, we're talking about light bulbs. And the voltage is split up among those resistors. So again, the voltage would add up to the voltage supplied. Now, parallel has multiple choice for path. So we go from the voltage source to this first intersection, and we have a choice. The current can either go through the first bulb or it can continue on its way. So that's what makes it parallel. There is a choice for the direction of the current to go. So if this bulb is out, the other two in the circuit will light. If both of these first ones are out, the third one can still light because there is still a complete path from the voltage source through that bulb and back to the beginning. Voltage is the same everywhere. Voltage is your pressure that's pushing the current along. So voltage is the same everywhere in a parallel circuit. Resistance drops. Now this is big about parallel. This is the huge advantage. Resistance drops as resistors are added. And if we go into the math, it's actually inverse. The addition of the inverses of each of the resistors is equal to the inverse of the total resistance. So when you add them up, you always end up with a total resistance that is smaller than any of these. Current is split up among the resistors. So if one bulb goes out, then you have more current for the other two or the other one. And the other thing that I do need to say about parallel, because we have a choice in direction to go here. We said that it's the same as like waiting to pay your toll in your car. If there's one gateway that's open, it's a very slow ordeal. So it's very slow going to get through the toll booth. But if two more gates open, now resistance drops and it's faster getting through the toll gate. So that's why when we're talking about a circuit, resistance is dropping. Ohm's law says V equals IR. So that means that the current is increasing. So over here, if your resistance increases, your current is dropping. Over here, if your resistance is dropping, then your current is increasing. All right, so it's the same. Current and resistance are inversely proportional, but here, when you add resistors, you're dropping resistance and you're increasing current. One other thing, in the sim that you did, was it a sim? No, it was the CER. When they're saying the bulb is dimmer, that means the current has dropped. I'm sorry. Yes, the current has dropped. The brightness of the bulb is an indication of the current. Do you have a strong current? Then you have a really bright bulb. Do you have a dim, a small current? Then it's dim, so it's not as bright. Let's go ahead into transformers. Actually, Faraday's. I want to say one thing about Faraday's. I didn't write anything down about Faraday's. We have gone over it before, but Faraday's law says that the number of loops. Do I have one that says Faraday's? No. The number of loops is proportional to the voltage that is produced or induced in a circuit. So the more loops you have, the more voltage you can produce. And you may have seen that if you did the nail lab. I haven't gone over that at all yet. That's due today, right? So with Faraday's law, we're going to use that to talk about transformers. So transformer starts with a primary. So I don't really want you looking at the second part of the board yet, but we have a primary coil of wires, and that's the input. That's your voltage source. So you're attached to a voltage source. Now we have a secondary coil. So that is not connected to the primary coil of wires. This is connected to a galvanometer, so that can measure your voltage. It's much more sensitive than a voltmeter. So if we have 7 loops here, I believe I drew 7, and we have 7 loops here. When we close the switch, right now there's no reading, but when we close the switch on the transformer, we momentarily induce a voltage in that second set of coils. That's my left hand, I can't do that. I can try, but it won't be very good. So when we close this circuit, we get a current that's happening in this coil of wires, and that induces a voltage over here, but only when it's changing. So that's only when you flip the switch. If you turn it off, again, it's going to produce a voltage. Momentarily, it's producing a voltage in the secondary set of wires. So that, because we're turning it off, it's changing the direction of the current. So it's going the opposite direction. The voltage is in the opposite direction. So what does that mean? Well, in order to make use of that technology, we know Faraday's law that the more coils you have, the greater the voltage that can be induced. So if we want to do a step-up transformer, we're going to have our primary that's connected to the voltage source, and we're going to have secondary, it's someplace else, that is also connected to, it is not connected to your voltage source. So on the secondary, I have 2 coils of wire. On the primary, I have 1. So can you see that the secondary has more coils of wire? That means we're going to be able to double the voltage from the primary to the secondary, because Faraday tells us that the voltage is proportional to the number of coils that we have. Now, there's also the ability to do a step-down transformer. So that means that we're starting with 2 coils of wire, or 2 turns of the wire from our voltage source. This is our primary on this side, and we're ending up with one coil of wire. So do you see that we're stepping the voltage down? So this light bulb that I have here, it only has 4 beams of light coming out from it, indicating that it's dimmer than this one that has 6. All right. So you may ask, why would we ever want to step down the voltage? Where is your electricity generated from? Is it down the block from where you live? Is there a power plant down the block? No, typically we put them way out in the middle of nowhere, far away from where the people need their electricity. We put them way out there because it's noisy. it's not pretty. So we don't want that equipment right in our neighborhood. So we have to transport that electricity a very great distance. But Ohm's law tells us that V equals IR. So the greater the resistance, the smaller the current is that you're getting out of it. When we're sending that electricity through the wire, the longer the wire, have you ever had to plug something in from really far away? If it's really far away, then you have to have a pretty heavy duty cord in order to get your current out of that because of that resistance. The other thing that happens if you have a long cord and you don't need all of it, you coil it up in a pile right by the outlet, maybe, and that pile gets hot, doesn't it? That's because of the increased resistance that's happening. So, because we're going such great distance, the resistance goes up so high that our current that we're going to get, we're going to be spending all that money and effort to generate that electricity, and then most of it's getting lost on the trip to your house. That doesn't do you much good. So the plan that we use is that we crank up the power so that the voltage is really high. So we know that power is V equals IR. I have to erase another board. There's no room on that one. So that our power, when we have a really large voltage, we have a really small current. Because we have a really small current, then we don't have high resistance because V equals IR. I'm sorry, power equals IV. So if our voltage is really large, then our current is going to be really small, and that lowers our resistance so that on the trip from the power plant to our house, we're getting most of that current back again. But can we use power that has really high voltage? Can we use that in our house? No, we have to get it down to 120. So we have to step it down. That's why when the power gets to your city, there's going to be a step down transformer. And then when it gets to your community, there's going to be another step down transformer. And those are much smaller than the high voltage wires that you see running out in the middle of nowhere. That transformer is going to be a smaller thing. And then that's what distributes the power to your home. All right, so I think that covers everything that I wanted to talk about. There's one more thing that, and I've said this before, but I do want to say it again, and I should write down Faraday's law for you also. I've written it down before, but this is in terms of loops. But that when we have a current, it's inducing a magnetic field and it's inducing a force. We talked about that with the right hand rule, that if your current is going in this direction, the magnetic field is in the direction of your other fingers. So that would be towards me. And the force is your thumb. So the force is popping out. If we have to do it in the other direction, if the current is in this direction, the magnetic field is coming towards you, so that we call that out of the page, and the force is down. Okay, so they are always perpendicular. The force and the magnetic field that are generated are always perpendicular to the current. And okay, the other thing was Faraday's law. I'll write that down as voltage is proportional to the number of loops. Okay, can I just have everybody say hi? Probably the same people as last time, but if you could just say hi, that would be great. And then I'll go ahead and sign off. If you have any questions, let me know. Hi. And then the other thing I wanted to see, and I kind of mentioned it last time, but I'll have to send out a survey. Maybe I'll send it on Remind to see if you guys want to do like an end of year virtual party, if we want to do a senior party or just everybody. Um, that's up to you guys. So I'll send out a survey on that in on Remind. Okay, it's a little early to think about it, but in the next week or so. Okay, bye bye, you guys. Thank you for coming. See you next time. So Monday at 11:30. Have a good weekend.